So when we first were exposed to determinants and how to compute determinants in our last session, the idea that we had is to use the elementary row operation, so to use row reduction in order to compute determinants, because we were able to say, here's what each of the elementary row operations actually does to the determinant of a matrix in the process of finding its reduced row echelon form. So let's suppose that I have this matrix right here, 2, 3, 1, negative 1, 4, 2, 3, 1, 2. I'm using a web page here that I think I must have learned from one of you, because it gives you the reduced row echelon form, and it shows you each one of the steps. So I'm sort of bypassing that process of trying to figure out all the steps on our own. And it turns out that to get this matrix into its reduced row echelon form takes 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. And by the time we're done with that ninth step right here, 1, 0, 0, 0, 1, 0, 0, 0, 1 is the matrix that we get at the end of the day. And so if I wanted to know what the original matrix's determinant was, then I would have to sort of retrace my steps and figure out how the eventual determinant is related to the original determinant. And so that's what we do when we do use this sort of clunky way of discovering a determinant. So what is the determinant of the identity matrix that we have down here at the end?
1.
Yeah, that determinant is just 1, right? The identity matrix does nothing to the volume of anything on which it acts, because the identity matrix does nothing at all. Whatever vector you give it, it just gives you the same vector back, right? So it's not changing volumes at all, so its determinant is equal to 1, because multiplying something by 1 is the same as not changing it, right? So the determinant is 1 by the time we get to the end. And of course, our interest is what was the determinant before we started the whole process. Right? So up here at the top, determinant of A equals whatever. So that's going to be the thing that we try to figure out. And so we reverse engineer the process. Starting from my matrix down here at the end, whose determinant is 1, we look at what are the steps that are being used to go from these matrices to these other matrices. So here we are subtracting a multiple of one row from another row. That's the same thing that we're doing the step that comes before it and the step that comes before that. So I'm going to highlight all of the steps in this process that are of the flavor add or subtract a multiple of one row from another row. And there's a lot of those steps. So what do we remember is the impact of the row operation that adds a multiple of one row to another row. How does that impact the determinant of a matrix?
It does not.
It doesn't. So the determinant doesn't change at any one of these steps that I highlighted. So that's a good start. That means that we don't have to do anything. We don't even have to see those steps in our computation. No change here, no change here, no change here, and no change here. Okay. Is there also a step in here where we swap two rows? There actually isn't. So this particular row reduction is carried out without any row swaps. But just to refresh our memory, if we did have a row swap, what happens to the determinant of a matrix?
You just change its sign.
We change its sign. It reverses from positive to negative or negative to positive. So if we had had a row swap, we would have to attend to that. But we don't in this case, which is kind of nice. And so all the steps that are left are steps in which what we're doing is either multiplying or dividing a row in place by a constant. Oops, looks like I missed one row operation, which is adding one row to another row. And so that's another no change. And so the only steps in our row reduction here that are actually changing the determinant at all are these steps that I'm highlighting in orange. Right? And so what happens when I, like we do in the first step here, if I divide row 1 by 2, in other words, I multiply row 1 by 1/2, what's happening to the determinant?
Is equal a half?
Yeah, the determinant is multiplied by half at that step. So the determinant is a linear function of the rows of a matrix. And so whatever I multiply a row of a matrix by, the determinant is getting multiplied by that same amount. So the determinant is getting multiplied by 1/2 at this very first step. So whatever determinant of A really is, by the time we have done our first step, this new matrix has a determinant which is half as big as my original matrix was. And so then I keep going, no change here, no change here. Oh, here I multiplied row 2 by 2/11. Oh, yuck. So then what happens to the determinant at that step?
You multiply it by 2/11.
Yeah, the determinant is multiplied by 2/11. This is, again, one of the irritating things about row reduction is that in general, it involves some nasty rational number arithmetic. 11/23 is what they multiplied row 3 by in order to get that 1 in the pivot position that they were ultimately looking for. So there's 3 steps here where the determinant is changing. Right? The first step, we multiplied the determinant by 1/2. And then this step, we multiplied the determinant by 2/11. This step, we multiplied it by 11/23. Right? So if I want to go backwards, I have a determinant of 1 here at the end. And in the previous step, because there was no change in the determinant, in the previous step, the determinant of this matrix must have also been 1.
1.
Because there was no change, exactly. So we're going to keep a running total. Here, take a step backwards. This determinant is 1. And then in the previous step, there was also no change. And so this matrix's determinant should be 1. But now if I go back one more step, I am crossing through a step that did change the determinant. So whatever the determinant was here, when I multiply that determinant by 11/23, the new determinant is equal to 1. So how do I go backwards?
Divide.
Divide. Instead of multiplying by 11/23, I want to divide by 11/23. And so the determinant of this matrix must have been 1 divided by 11/23, otherwise known as 23/11. As I say, clunky, right? We're going to go back another step. There was no change here, so we're going to keep that same determinant, 23/11. There was no change in the previous step, so that determinant is 23/11. Okay, and now we've encountered another step where the determinant does change. And instead of multiplying by 2/11, because that's how we got here, I want to go backwards, dividing by 2/11. And so if I go backwards, dividing by 2/11, it's the same as multiplying by 11/2. I'm going to write that out, 23/11 divided by 2/11. So that determinant is 23/2. Everyone agree with that?
Yep.
Okay. So then, step before that was no change, so that must be 23/2. The step before that was no change, so that must have been 23/2. And so now we only have one last step to go backwards. And that's the step that's going to land us at our determinant of A. And for that, we just have to reverse our multiplication by 1/2 by dividing by 1/2. And when I divide 23/2 by 1/2, I get 23. So the determinant of my original matrix must have been 23. So a little bit clunky, but at least it gives us a way to get started, right? Knowing how the elementary row operations affect the determinant of a matrix is actually a pretty good way to turn a matrix which we almost know its determinant. If we could just do one row operation and then we can figure it out, then we know how that row operation is going to affect the determinant of the matrix. So our goal for our next steps is going to be to figure out how to identify which matrices might actually be easier to take determinants of by reducing the dimension of the matrix of which we have to take a determinant. So our next set of techniques is going to be, how do I relate the determinant of a larger matrix to determinants of smaller matrices? So it's almost, if you're a computer science type person, it's a recursive algorithm, right? We have a n by n matrix, and I want to find its determinant, and so I want to express that n by n determinant in terms of n minus 1 by n minus 1 determinants. You asked me to compute the determinant of an 8 by 8 matrix, and so I write it out as a bunch of 7 by 7 determinants. And for each of those 7 by 7s, I'll write that out in terms of 6 by 6s. For each of the 6 by 6s, I can write it out as 5 by 5s, blah, 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 until I get all the way down to 1 by 1 matrices. And this was a question that I know we addressed last week. And the determinant of a 1 by 1 matrix is just that number that's sitting inside the 1 by 1 matrix. So it's a recursive algorithm that actually gets us easier determinants as we go along until we get all the way down to the 1 by 1s, which are the easiest determinants in the world. All you do to take the determinant of a 1 by 1 matrix is just rip the brackets off the matrix, and you have the determinant sitting right there. So that's what we're going to move into next.